Okay, so we have our emulators, we have our diagnostics, we're presumably satisfied with them or else we wouldn't be carrying on any further. And the final part of the emulation history matching process, of course, is to propose a new set of points in order to train some more accurate emulators, etc., etc. Now, if you were here yesterday, this will look very, very similar. We have one function which we use to generate new proposal points, and it is this generate new design function. And this works exactly as it would in the deterministic case. We give it a set of emulators. Here, we've just given it the full list of emulators. Again, like I said earlier, if we have targets for variance emulators as well as mean emulators, it will take that into account. Otherwise, it makes the assumption that we're matching to the means. We give it a number of points that we want, and we give it our targets. And in principle, we can give it a whole host of other things. If you're interested, check the help files. There are a few other bits and pieces that we can do. But crucially, this will follow the same sort of steps as in the deterministic case. Tries to generate a very large Latin hypercube across the space, does some rejection sampling, draws some lines out between pairs of points to try and find the boundaries of the space, and then fills out the space uniformly using a variety of different techniques. So once it's done this, well, the idea here is, as we started, when we built up this model, we decided we wanted 100 points to train with and 50 to validate with. So we're going to ask it to generate 150 points for us. We have our targets, etc., etc. If we run this, it will chug along. If the acceptance rate is suitably high and we don't need to worry about doing anything other than making a big Latin hypercube and rejecting, then it will do that as many times as necessary to fill out the space. In general, it's worth remembering, I mean, this can take a little while, but even though we're looking for 150 points, typically it's checking 10 times, 100 times more points. And this is kind of where the emulation comes into its own, because we wouldn't necessarily be able to check a very big Latin hypercube using the model. Particularly, I think each run takes, depending on your laptop and depending on your architecture, maybe like 4 or 5 seconds per run. It would take a very long time to do that for a large Latin hypercube. So this allows us to rule out massive swathes of space without really having to worry about it too much. Once we've got them, well, in principle, that's our wave done. We've done our first iteration of history matching. We can stick these back into the model, and we can start again from, I guess, section 4, chug through, and do another wave, etc., etc. At the end of a wave, it's probably always useful to have a look at what's going on and to see what we get. And we can use plot wrap, which is just a nice little wrapper around the normal R plotting function, just so that we can make sure that our bounds are the actual ranges we started with, which is quite helpful to avoid zooming into space and getting confused about how big our remaining parameter space is and stuff like that. So if we do that for this, well, we see something fairly reasonable. We see that a few of these parameters, particularly the most influential parameters, if you remember, are active variables, particularly for the variance, as well as for the mean emulators, was beta1, was epsilon, and was gamma. And if we look down those columns, we can see that we've started to reduce the space on the left-hand sides of those. Particularly gamma is being quite heavily restricted. We've removed about 50% of the space just in that parameter alone. We can also start to see some potential correlation structure between some of the parameters, particularly beta1 and epsilon. We can see these starting to behave a bit more constrained. Some of them haven't necessarily changed too much, and that's usually the case. In the first wave, you don't expect to be able to completely restrict all parameters. And again, there is the sort of argument, you might do 5, 6, 7, 8 waves of emulation, and some of these parameters, at least univariately, are not being constrained. That's not necessarily surprising. A lot of the times with these models, it will matter whether they are correlated. Maybe one has to be high and one has to be low, but you can swap those around and it ranges right the way through. So you might end up with this kind of uniform looking like projection onto a single parameter. But we can have a look. We see, well, there are a couple of things there. We can see that some things are being restricted. We can see that this space is roughly kind of uniformly sampled from generate new runs. And if you really want to, although I think we made the ranges wider for the stochastic model, but we can kind of see a couple of things if we look at yesterday's similar results. So this was again after one wave of emulation doing the deterministic equivalent of the model. One thing to note is we still have this relationship between beta1 and epsilon, but it's slightly more diffuse in the stochastic case. That again isn't terribly surprising because we're not just contending with the actual model output, we're contending with the fact that this is stochastic as well. So this is kind of exactly in line with our expectations. Cool. So yeah, and again, because generate new design does in the sort of underlying stuff use a large Latin hypercube, the same sort of arguments run about setting seeds and randomness in R. So if you run generate new design, your points won't be exactly in the same place as mine have been, but you will probably see exactly the same sort of structure showing up. Cool. Yeah, and you're welcome to just take that code, run it, see what happens. It will probably chuck out something very, very similar and in a relatively short amount of time. Just to quickly mention, this is something I think we mentioned yesterday as well. There is a function within the package that kind of automates this process. So we would not necessarily advise just jumping in and doing waves emulation, history matching without investigating the emulators, thinking about the space. None of what we have made is any substitute for expert knowledge, expert intuition into models, and that is always going to be a crucial part of this, right? But there is a function in the package called full wave, which will try to do all of these things for you. So if you give it some data, so the data set, if you're doing it deterministically, it would be just a single result per parameter set. If you're doing variance emulation, it will be all of the repetitions. You give it the list of ranges, which is again that named list, and you give it the targets in whichever form we want to give it. So either the value with some uncertainty or these lower upper bounds that we've been using today. And that will train the emulators. It will try and split the data into a training and a validation set. It will do the diagnostics. It will try to ensure that the diagnostics are passed or throw away emulators that don't pass it. And it will propose some new points for the next wave. So if you're interested in kind of playing around with that, feel free to, again, !full wave in R will give you the help file for it and a couple of examples of using it, including using it for later waves.